Mr. Tarrou, in this algebra lesson, we're going to be looking at 4 examples involving the difference between speed and rate of change. They're basically just another way of saying slope, but we're going to be having, or calculating, this slope in a word problem scenario. And when you are looking at the difference or comparing a change in distance over a change in time, well, we're looking at that often in a scenario of speed, like your car's speedometer. It tells you how far you're moving over a given period of time, and that's going to be miles per hour or kilometers per hour. Now, the one thing to note, right, if you have looked at a speedometer in a car, you are only going to see positive values. Now, since this is only an algebra lesson, we're going to be comparing, like I said, speed to rate of change. Well, when you're talking about Algebra 2 or pre-calculus, or I talk about it a lot in my calculus class, we deal with the difference between speed and velocity. Now, velocity, like a rate of change, can be either positive or negative. Like if I'm in my car and I put it into drive or first gear and I go forward, say 5 miles an hour, then my speed and my velocity would be said to be positive. But if I put my car in reverse and go backwards, I'm thinking sort of like in my calculus class, if I'm moving to the left, my velocity is going to be negative. But as I look down at my speedometer, actually I should be looking behind me, right, so I don't hit anything. But if I were to go backwards and look at my speedometer, it's still going to say maybe that I'm moving at 5 miles an hour. So whether I'm going forwards or in reverse, my speedometer is still going to give me a positive value. Well, that's not true with a rate of change. A rate of change is just any change in whatever variable is along your y-axis over the change in x, whatever variable is along your x-axis. Now, as we go through our 4 examples, they're all going to be related to, you can see example 3 here, looking at distance over time, but rate of change can be calculated between any 2 variables that you're measuring, and the value can take on either a positive or negative value. If we're looking at rate of change and it's not a word problem, or we're just simply graphing a line, say y equals 2x plus 3, we can say that it's a change in y over a change in x if your textbook is using this sort of triangular or what we call delta notation. Of course, if you're moving vertically, you're going to have that change in y. You calculate a change through subtraction, so y2 minus y1 over x2 minus x sub 1, or we just know that 3-word phrase, my students know this very well, that slope is rise over run. Well, rate of change is really just slope, but we're incorporating that units of measure, both in speed and in rate of change. These are all going to be sort of in an application setting of rise over run. So speed can only be positive, and rates of change can be either positive or negative. And when you later learn the idea of velocity, same thing will be true there. Okay, so what's this going to look like? As we go through the 3 or 4 examples, we'll have timestamps in the description, and we're going to be calculating these speeds and rates of change off of this graph. So determine the speed and rate of change for each time period, and we have our time periods marked off as 1, 2, and 3. So question number 1, what's the speed and what's the rate of change for this moment in time between time 0 and time 2? Okay, well, whether it is speed or whether it is rate of change or whether you're calling it slope, it is rise over run, which is a very nice way of hearing this and seeing this when you're looking at a graph. To get from this point of, well, 0, 2, and by the way, my graph is sort of intersecting the y-axis here at the value of 2, so that would also be called an x-intercept, a y-intercept. Whenever your x value is 0 in a coordinate, you're looking at the y-intercept. So we go from time 0 and a distance of 2 feet from some object to when we're 2 seconds farther down through time, 2 seconds later we are, well, 7 feet from the object. So we're here at 2, 7. Maybe we'll do this y sub 2 minus y sub 1 over x sub 2 minus x sub 1 formula right now. Rise over run. So we're going to rise up with a maybe orange chalk so it shows up better, I hope. We're going to rise and run. How do we get from this point of 0, 2 to 2, 7? Well, we go up. Now you put your pencil down and you don't count. You start counting when you move. So from 2, we're going to go up 1, 2, 3, 4, 5, and then we're going to run over 1, 2, 3, 4. So we have moved a total of 5 feet over this. Now I said 1, 2, 3, 4, and I almost made a crucial mistake, a critical mistake that my students make all the time. Hey, when you start looking at a graph and identifying how much you've risen over how much you've run, your rise over run, make sure you pay attention to the units of measure that are along the x and y axis. Now I've correctly identified this as 0, 2, because I looked at 0 and I went up 2 and I said that's 0, 2. I've identified this point as 2, 7 because I looked along the x-axis, which has the variable of time in seconds, and I went up from 2, or from 0, 0, the origin, over 2, and then up to the y-coordinate of 7, and I wrote 2, 7. But when I was just starting to count that rise over run, I counted up 1, 2, 3, 4, 5 lines, and I counted over 1, 2, 3, 4 lines. Well, that's not correct because each one of these lines does not represent one unit of change. We go from 0 to 1/2 to 1 to basically 1.5 or 1.5 to 2. So every 2 lines is representing a change of 1 second in time. So as I run over, that's actually 1 second and then 2. I'd like to say I made that mistake on purpose just to be able to talk to you about that, but it actually was an honest mistake. It happens. So be careful with your work. So our speed is 5 divided by 2, or it's 2.5. Now 2.5 what? When you say slope, you can say that a slope is, well, 5 halves, or 2.5. And by the way, now that I have taken this 5 divided by 2 and divided it out and wrote it as a decimal, the decimal does not make this a unit rate, but the fact that the denominator now is 1 makes it a unit of rate. And I can describe what this number means actually as a unit rate better than as simply rise over run. Rise over run is really only good for graphing a line on an XY axis. So what does this 2.5 mean? Well, it means that we're covering 2.5 feet. Now division in math means per, so it's 2.5 feet per, well, there's no denominator, so it must be per 1 unit of change on the x-axis, which is measured in seconds. So it's 2.5 feet per second. My speed is 2.5 feet per second between 0 and 2 seconds, or for the first 2 seconds in our graph. Well, what's the rate of change? Because the rate of change can take on both a positive and negative value. Well, we're moving away, or we can see, maybe if you've talked a little bit about slope for graphing lines, that our line is rising. As our x values increase, our y values increase. Our line is going up to the right. Well, that's a positive slope, and thus our rate of change is positive. The rate of change is actually here exactly the same as the speed. The rate of change is 2.5 feet per second. Now, what if you didn't want to count that rise over that run? If you really like that slope formula and you want to say, well, I know that slope is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's something I'm familiar with that we've already covered in class, or maybe it was a previous class, like I've noticed that my Algebra 1 students have had a lot of experience with this with their pre-algebra class. You want to identify a couple of those coordinates and decide which one you want to call point 1 and point 2. Maybe this is point 1 and this is point 2. Okay, well, if that's the case, now that we have our labels as point 1 and point 2, and you can call this point 1 and this point 2, really where you put these labels is really not important. What's important is how you do the subtraction. You can take your y sub 2 value, which is 7, and then take your y sub 1 value, which is, well, yeah, we started 2 feet away from some object, over x sub 2, which is 2, minus x sub 1, which is 0. And of course, we get that same 7 minus 2 is equal to 5 over 2 minus 0, which is equal to 2. That 5 halves that we noticed by counting up 1, 2, 3, 4, 5, that change in y over the run, the change in x, which is 1, 2, or it's 1 and a half, 1, 1 and 1/2, and then finally 2. But either way, our rate of change is positive 2.5 feet per second for the first 2 seconds. Well, all right then. What happens here at time 2? There's no change in the distance that we are from an object between the seconds of 2 and 6. So what is our speed? And in this will be a case the rate of change is also the same, because it's going to be, well, the change in y over the change in x for rate of change. The distance that you are from an object over the amount of time that has gone by. Well, here we're at 2 seconds, we're 7 feet away from an object, and at 6 seconds, get the same color, we are still 7 feet away. You might already know the answer, but we're going to go ahead and talk about rise over run. From here, moving to the left, and when you visually identify rise over run, if you will, from graphically, from graphically, from a graph, you always want to move left to right, like you read in a book, at least in the English language. So from here, we do not move up or down at all, because we're already that 7 feet away from the object, and we maintain that 7 feet away until we're at 6 seconds, and then there's some kind of movement that happens, but we'll talk about that in a second. So our rise is 0 over the time period between 2 and 6. Well, 6 minus 2, or just count it out, 1, 2, 3, 4. And while you can't divide by 0, you can divide any number into 0. 4 times what is equal to 0? Well, of course, the answer is 0. So our speed is equal to 0 feet per second during or between 2 and 6 seconds. And I'm kind of just writing over the rate, because when your speed comes out to be positive, well, so will your rate. Okay? Remember, speed can only be a positive number, and rate can be both positive and negative. So if speed is coming out to be a positive value, well, then the rate is going to be the same thing. When are you traveling a certain, speed, or have a certain rate of change? Because our rate of change is, and our speed is changing through the different time periods of this graph. We're not constantly going 2.5 feet per second. We're not constantly forever along this graph here, as it's shown, not moving at all, or having a speed which is 0. And by the way, you can see that unit rate as well here, that in 1 second for the first time period, in 1 second we go from 2 to see where, I tried to draw this pretty neat, we're between 4 and 5. Well, right, if it were, and it's supposed to be, drawn right in the middle, that's 1, 2.5, or 2.5 units of change in y per 1 unit of change in x. That's really the definition of slope. The amount of change in y per 1 unit of change in x. That's how we define slope in my pre-calculus class and in my AP statistics class, but in my Algebra 1 book, it's called a unit rate. It's great for explaining what this number means in context of the problem. Rise 5 and over 2, well, we can say I've moved, I'm kind of going back here, but we moved 5 feet away within 2 seconds. That tells a story too. But when describing or interpreting slope for a word problem, it isn't that usually that unit rate idea, or change in y for 1 unit of change in x. Now, for our last part of this example, we're going to talk about the speed of the object and the rate for time period 3. Well, at 6 seconds, we're 7 feet away from an object. Now, over here, way over here at 10 seconds, we have moved some. We've gone closer. Our line is going down. Our distance away from some object is decreasing. Okay. So here we're going to start to see a difference between how we report a speed and what in general is a rate of change, even if that rate of change is still distance over time. Well, we're at 6, 7. let's do this graphically instead of identifying this point, which we can anyway. It's 10, comma 5. But let's see, get our orange chalk out again. How far down and over do we have to move to get from this point here further to the right in our graph? Well, we have to go down. And if you go down and you think of, fine, it's okay to say slope is rise over run. When you rise in a negative or a downward fashion, it is a negative movement. We're getting closer. 6, excuse me, our y coordinate is 7. 7 minus 2 gets you down to just simply 5 feet away from an object. So that is a rise of -2, and then we're going to run. And again, as you count the lines along the graph paper, if some is given to you in a problem you're doing, don't just start automatically counting, 1, 2, 3, 4, 5. You might be counting by 1, and you might be counting basically by a half, like we are in this picture, 3, 3.5, 4, 4.5, 5, and so on. You might be counting by 5s, 0, 5, 10, 15, 20. Make sure that you are looking at that scale as you move along with your rise over run, visually identifying some information off the graph. So that's 1, 2, 3, 4. So we have gotten closer to our object by 2 feet over a 4-second period. So our speed is, well, okay, now, hold on. Our speed can only take on a positive value. So we have moved 2 feet over that 4-second time period. So our speed is 2 over 4, or 1/2, or 0.5. I personally, as a math teacher, like the fraction better, but 0.5 feet per second. Or you could say, that we moved 2 feet in 4 seconds. Now, as a rate of change, though, rate of change can take on a positive or negative value. Here's where the rate of change is going to bring in the idea that we're getting closer. We moved down. We went from 7 feet away to 5. So our rate of change is -2 feet per or over a 4-second period. Well, that now comes out to be simply -1/2 or -0.5 feet per second. Now I'm going to step off here and, like I did in my first example, kind of interpret what these numbers mean in a sentence, or like a little mini story, if you will. How can I use these two values in a description of this time, of this movement over the last 4 seconds, from second 6 to 10 seconds after we started the stopwatch? Basically, hey, you're 2 feet away. Click. For the first 2 seconds, I move up to 7 feet away, or 2.5 feet per second. Then for the next 4 seconds, we're standing still between seconds 2 and 6. And in the final 4 seconds, we start moving back towards whatever this object is that we're measuring our distance from. Alrighty then, so our speed is that 1/2 feet per second, and the rate of change is -1/2 feet per second. So how do we interpret these numbers into the context of the problem? Well, we can say that we move towards something at 1.5 feet per second between the time period of t equals 6 and t equals 10. You might be able to say just the last 4 seconds as well. Or you moved at a rate of -1/2 feet per second, again between those seconds of 6 and 10. What you don't want to say is that you moved towards at a rate of -1.5 feet per second, because the towards is already saying that your distances are going down. But then if you also come back with a -1/2 feet per second, the towards and the negative, they kind of cancel each other out. So moving towards something at a negative rate, that would actually mean that you're moving away. So if you want to use that positive number, which is the speed, again, kind of thinking about how I talk about velocity in later math classes, speed, like the speedometer on your car, does not indicate what direction you're going in, whereas velocity, or effectively rate of change, does. So if you're going to say, I'm moving at, my speed is 1.5 feet per second, you do want to incorporate, whether you're moving towards something or away, because in that I've erased it now, but the speed for segment 1 was a positive 2.5, and the speed for segment 3, which is that negative slope, getting closer instead of farther, well, the speed is still positive. So the speed, honestly, of an object, of some movement, can legitimately be confusing because it doesn't tell you what direction you're going in, like the rate of change, or when you learn that vocabulary of velocity will do for you. So we're moving towards something. That first segment was moving away at a particular speed over a particular period of time. The rate, though, the sign indicates that movement. Don't mess yourself up by saying in this example towards with a negative rate at the same time. That's really technically incorrect. Now, we're going to look at our next page of notes. Basically, we're going to talk about an average rate of change for our last example. And we're going to talk about, how we can look at a graph and just from the steepness of the line segments, see that, if a line segment is more steep, it is going to have a higher speed. So again, if you have a steeper graph comparing distance to time, the steeper that graph is, the faster the movement. The more distance, the vertical, what's on your vertical axis, has been covered over a particular period of time. And the less steep, whether it's with a positive slope or a negative slope, a positive rate of change or a negative rate of change, you are covering less distance over that period of time, so that is a slower movement. And then finally, if you're looking at, again, just at a comparison between distance over time, if you have a horizontal line segment, then there is no movement. The distance is not changing over that period of time. And I do make that footnote about comparing distance to time because maybe your vertical scale is a particular speed or rate of change. And of course, you can be comparing any two variables that are quantitative, just numerical, on a scatter plot or graph. So this is just specific to that distance over time. If you have a linear segment or a line within your graph comparing distance to time, then that is what is called a constant rate of change or a constant speed. Now, if you have something like we have over here, which is a graph where we start off, we don't actually know where we start off at because this arrow just goes up forever, but at 1 second after we've started the stopwatch, we're 12 feet away from an object. And we do not have a linear segment here, so we do not have a constant rate of change. Now, in the previous example, we had 3 line segments, so we had sort of 3 time periods where we had 3 different constant rate of change or 3 different speeds. Well, here we don't have any portion of this graph which is actually linear. So we're going to still effectively find the rate of change or the speed, if you want to just report a positive number, or a slope, if you will, but we can't call it rate of change or speed or slope because, well, it's forever or constantly changing. So what we're going to use is this idea of average rate of change. So we have a very steep, a very fast rate of change, but as time goes on, that sort of becomes less steep or slows down. And I'm tired of hearing my shoes squeak on the floor, so I'll just take those off. Let's find the average rate of change between the first 2 time periods. I already have an m sub 1 and m sub 2 here, but I didn't label it on my graph, so let's do that. We're going to have this represent our average rate of change for our first time period, and we have that point of, and now I did this on purpose here. I have numbers showing up every other spot like I did in the previous example, but we're counting every line segment, right? We go 2 segments, and that is a change of 2. So every one of these tick marks does represent 1 unit of change. So we have 1, 12, which is now very sloppily written. And we have here from the origin to the right 1, 2, 3, and up 6. And looking at that graph, thinking about slope or rate of change is rise over run. Read that left to right, left point to right end point. how much do you have to rise where you're going down, so that rise value is actually some kind of negative number, and how far are you running to the right? Well, boom. 1, 2, 3, 4, 5, 6. Start counting when you're moving, or of course at y sub 2 minus y sub 1 over x sub 2 minus x sub 1. 12 minus 6 is equal to 6. So we've gone down 6 units of change. And, well, I got the coordinates up here. Let's do x1, y1, and x2, y2. Just hit that formula as well. Average rate of change is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So we have that 12 minus 6, like we counted off, and then I just verbally said, over x sub 2 minus x sub 1. X sub 2 minus x sub 1. Now don't place these numbers thinking you have to have a positive answer. Yes, if this comes out to be negative, our speed, our average speed, would be said to be positive, but rate of change is allowed to be negative, and that does happen. Yeah? If your distances go down over time, if your lines go down to the right, you have a negative rate of change, a negative slope. So 1 minus 3, that comes out to 12 minus 6 is 6. 1 minus 3 is negative 2, and that is negative 3 feet per second, or we came down, oh, and by the way, when I looked up here, I came down, my rise was a negative number, and my run was always positive. I always, when doing rise over run, off of a graph, read that left to right, period. Well, when I look here, I guess you can say you go back in time, or you can move from right to left, and if you move right to left, your numbers are getting smaller, effectively a subtraction. You know, we can go back 6 and up, or back 2, excuse me, and up 6, but reading that left to right, you know, it does not matter where you put a negative sign in a fraction, whether it's in the top, middle, or the bottom, that whole fraction is still negative. So I'm going to just float that negative up to the top. It numerically means the same thing, but as far as reading the graph and having that negative rise over that positive run to the right, it matches the way we're looking at the graph, and that is negative 3 feet per second. Or my speed is moving towards something at 3 feet per second between the time periods of 1 and 3 seconds. Now for our second time period between these 2 points, and let me just pick a different color, purple, we've got 5, 3 and 10, 1. We've got 0.1. Just one more time for you, 0.2. I'm doing this twice for more practice, plus the idea that average rate of change is forever changing. If you pick a different time period, you get a different answer, which is why it's important for you to describe where on a graph you are finding your speed or rate of change from. So y2 I've labeled as 1, minus y1, which we've labeled as 3, over x2, which is labeled as 10, over x sub 1, which we've labeled as 5. That's negative 2 over 5, or negative 0.4 feet per second. But the average rate of change for this entire graph is not negative 3 feet per second. The average rate of change for this graph is not negative 4 feet per second. These are only appropriate for the time periods between 1 and 3 for our first answer, and between seconds 5 and 10 for our second one. So to turn this whole graph into a story, an interpretation in context, bam, picture in picture, old school way. We started moving towards something quickly, because we have a very steep portion of this graph at an average of 3 feet per second. I almost said average rate of change, but I've incorporated the idea of moving towards or away from something. So I'm almost really, because I'm saying towards or away, giving you a speed, right? The rate of change was negative, and all of a sudden I'm writing it as a positive number because I've included the word towards. So between seconds 1 and 3, now this movement gradually slowed down because it's becoming, you can see that gradual slowing of the movement, again, time over distance, because it's becoming less steep. So gradually slowed down to approaching some object at an average of 0.4 feet per second between the time periods of 5 and 10. And this is an interpretation or a story of explanation, if you will, of what's going on in this graph in its totality. And that is the end of my last example. I hope I've helped you understand the difference between speed and rate of change. And again, coming up later in some of your math classes, you will be comparing speed to velocity. Now, rate of change is just any rate of change, the change of any y over the change of any x. Velocity is just speed, so it's still going to be distance over time, but if you're moving to the right or up, you're going to have a positive velocity. In this case, we would be talking about moving away for something. And if your velocity is negative, then you're moving towards something. Or in higher level classes, maybe that's a movement to the left on an XY coordinate system or down. I'm Mr. True. Bam! Go do your homework.